Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a good day. I am going to present about my final year project 1 proposal, and my title is Salinity Gradient Solar Pond Maintenance and Operation. My name is Muhammad Amin bin Zahran and I am supervised by Insignia Technologist Dr. Baljit Singh. Let's get started. There are plenty of sources of energy. The most widely used is fossil fuel and coal. This type of resources, while still abundant, will eventually run out. The environmental impacts produced by these options are also a concern where pollution is very likely to occur. Looking at renewable energy resources, as opposed to non-renewable energy, they are seemingly endless and does not run out with use. One of the most well-known is solar energy. The sun produces vast amount of heat and light energy every second. The main question is how do we convert it into useful energy? This is where this study comes into place. Using a solar pond, it enables thermal energy to be stored passively without any external effort, excluding the setup, monitoring, or maintenance phase. In comparison to a photovoltaic cell, also known as a solar panel, where sunlight is directly converted into electricity, solar ponds allows thermal energy to be stored directly to be later used for other purposes. Regarding my topic, salinity gradient solar pond, first we must know what are solar ponds. What does it mean by salinity gradient? What types of salt are used? What are solar ponds used for? These questions will be explained shortly. First, let's look at solar ponds in general. Solar ponds are pools of water that traps solar thermal energy. The most common and widely known is salinity gradient solar pond, also known as SGSP. There are also other types of solar pond that I will briefly explain. The working principle of most solar ponds are similar, where water levels are separated to prevent heat loss through convection, with some factors differentiating each of them. So let's start with SGSP. It works by using a different salinity level to create a gradient and zones inside the water. I will show a neat little illustration. This is a water container. So the most bottom layer, also known as LCZ, lower convective zone, it consists of a saturated salt solution. This means that for every 100 grams of water, there are 30 grams of dissolved salt. The middle layer, also known as non-convective zone, NCZ, it has salinity gradient, where the salt level decreases with height. The topmost layer, known as the upper convective zone, it consists of fresh water. The different salinity levels change the density of each domain of the fluid, and these fluid domains does not mix with each other. This means that convection cannot occur between the different zones. This allows thermal energy to be stored at LCZ, and the temperatures can reach up to 90 degrees depending on climate. Next up is a viscosity stabilized solar pond, also known as gel solar pond. Instead of using a salinity gradient to separate water levels, this pond uses a polymer gel. The LCZ is still using a highly saline water to allow the gel to float on top. The density of the gel must be higher than the density of the UCZ on top so that the gel does not float. And the density of the gel must also be lower than the density of the LCZ so that the gel can stay in the middle and acts as a non-convective zone. The third one is shallow solar pond. As the name suggests, the pond uses a very shallow depth, and the water and the pond will be enclosed inside a film of plastic to prevent heat loss through evaporation. And last but not least, partition solar pond. The main difference between this and the earlier types of solar pond mentioned is that the zones are physically separated by a solid wall into different compartments. Rather than using a different density fluid to separate. Salinity gradient solar pond, as the name implies, uses salt to create different salinity gradient. By definition, salt is the byproduct of a chemical reaction between an acid and a base, the other byproduct being water. There are different types of salt, many different types of salt. The most commonly known is sodium chloride, also known as table salt. This is the type of salt that is used in salinity gradient solar pond. There are also other types of salt such as lead nitrate, calcium chloride, and potassium chloride. Not all salts are water soluble, and the types of salt that do solve in water does not always have a steady property. By referring to this graph, it is shown that every type of salt listed here have different solubility with respect to water temperature. For example, if we were to use cerium sulfate, this one right here, the solubility of the salt actually decreases with increase in water temperature. This means that the salinity level of water will decrease when the temperature rises. This will cause the LCZ to lose its density and disrupt the different fluid domains. The other type of salt, if we were to use, say, potassium chloride, which is this line right here, while it shows an increase in solubility when temperature increases, the changes are very drastic. So if the temperatures do drop, the solubility of the salt will decrease, salt crystals will form, it will disrupt the fluid domains and disrupt the physical properties of water. In comparison, when using sodium chloride, the solubility stays almost uniform no matter the temperature, from freezing all the way to boiling point. This steady property is the desired property in construction of solar ponds. There are several locations around the world that utilizes solar pond on a large industrial scale. Take these 3 solar ponds for example. The first solar pond is located at Victoria, Australia. The solar pond is used for salt production. The heat from the solar pond is extracted to preheat air that enters a salt dryer. The extra heat addition from the solar pond reduces the energy required to heat up the salt dryer. Next one is a salt gradient solar pond that is located in El Paso, Texas. The solar pond has an area around 3,000 square meter that operates along with an organic Rankine cycle engine to produce around 70 kilowatts of electrical energy that is supplied to the grid. The picture on the far right is one of the largest solar pond in the world, located in Beth Arava, an Israeli settlement. The solar pond has an area over 200,000 square meter and it aims to produce around 5 megawatts of power. The objectives of this project is to design and simulate the performance of SGSP. The study will be conducted on a much smaller scale for convenience. The maintenance of SGSP is also meant to be reduced, such as the condition of water, such as the clarity, the acidity, the salt gradient, and also the condition of the solar pond in general, such as insulation of wall or leakage problems. Lastly, The third objective is to increase thermal performance of SGSP. Solar ponds are known for their extremely low efficiency, which will be explained in later problem statement. This study aims to increase the overall thermal efficiency of solar pond. Moving on to problem statement, the first one is choosing the right type of working fluid. These types of fluids are chosen based on factors such as boiling point and the ability to be a reliable solvent. For solar ponds, the obvious fluid of choice is water. This is because water is abundant, it is available everywhere, it is chemically safe, stable, it is an excellent solvent, and it has a large specific heat capacity. The only downside is the boiling point of water. While being at a respectable 100 degrees Celsius, it is still relatively low compared to the ambient temperature. And thus, the low difference in temperature will result in having very low efficiency. If we were to choose a different type of fluid, such as cooking oil, another abundant type of fluid, it has a much higher boiling point compared to water, around 300 degrees Celsius. While this may be an upside, while it may be a good thing, oil is less dense than water and it will tend to float, no matter if the water is saline water or fresh water. Moreover, salt cannot be dissolved in oil at all. So, establishing a salt gradient using oil is out of the question. So, water is the obvious fluid of choice due to its availability, its reliability, and the desired physical and chemical characteristics of water. The next one is working area. Due to having such poor efficiency, a solar pond requires a huge surface area in order to be feasible on a large industrial scale. For instance, the solar pond located in Australia and Texas is around 3,000 square kilometers in order to sufficiently supply heat and work properly. In comparison, that is slightly larger than 2 Olympic-sized swimming pools placed side by side. That does not take into account the extra equipment needed for heat extraction and usage. Solar ponds does require maintenance, such as when leakage happens, or when the salinity gradient is disrupted due to external factors such as the weather and climate. Usually, the pond has to be emptied before refilling again, and this process can be very costly, especially on larger industrial scale solar ponds. For this project, when doing performance simulation, the simulation is done under perfect theoretical conditions. The results that will be obtained will not take into consideration the climate of the area chosen and other factors such as rain or wind. This is the flowchart of my proposal journey. Basically, it briefly illustrates the process of this project from beginning to end. It starts by reading research articles and writing literature reviews to select suitable parameters. Next is designing model for SGSP using a 3D CAD model. After that, boundary condition will be selected when using ANSYS software for simulation. When results are not acceptable or not accurate, parameters are changed and the process will be repeated. When the results are accurate and acceptable, additional parameters will be added to modify and improvise the results. This is the 3D model that I have made using CATIA software. The water tank will have an internal diameter of 1750 millimeters, a thickness of 20 millimeters, and a height of 1500 millimeters. The reason I have used a cylindrical water tank instead of a rectangular tank is because of the surface area of the side wall. For example, if we were to take a square shape with a length and width of 2 meters, we will get the perimeter of the entire wall. It will be around 8 meters. In comparison, if we were to use a cylindrical tank with we're having a diameter of 2 meters, the perimeter will be around 6.5 0.28 meters. That is significantly less surface area exposed compared to using a square wall. For the square wall, the surface area is larger, causing more fluid to be exposed and more heat loss through walls will occur. After choosing a suitable parameters, SGSP model will be simulated using ANSYS Fluent to obtain baseline results. The temperature of the LCZ is expected to be higher than the temperature at UCZ, NCZ, and the ambient temperature. With modifications like adding insulation on walls and the ground, the temperature of the LCZ can be further increased. And that concludes the presentation for my proposal. For any inquiries related to my proposal topic, feel free to contact me using my phone number or my email. Thank you and Assalamualaikum.